All right, so um, welcome to the lecture where I'm going to go through some of the topics that we're talking about in lectures this week at the code level. In the repository, there are 3 projects. One is C12 LERP, C13 rotations, and C14 Quaternions. I'm going to go through these examples specifically at the application level, and hopefully give you a bit of understanding of what's going on and how this stuff works. I'm going to zoom in a little bit more just so that you all can see. So first thing, let me build this project, which should be already built, and let's run it. So this is the LERP example, and you can see here that what's going on is we have this cone, and the cone is moving from one position to another position. You can see that when it has a longer distance to cover, it goes a little bit faster. When it has a shorter distance, it goes a bit slower. And cool. Yeah, we can kind of see that it's working out pretty well. So let's kind of look at the code that makes this possible. So the first thing we can see, so let's take a look at the code here. And so you can see LERP, this project, it has my mesh already in here where we can create the different things like generate a cube, generate a quad, generate a sphere, all those good things, fun stuff. So this is sort of the stuff that you've done before. We have the controller configuration code here, which if you're using a game controller, it gives you the ability to map those things to each other. We have the GUI as well. If you're unfamiliar with these things, I did post a video from Alberto that explains this. This is his code base, his sort of framework that he's built up for this class in previous sections and years. So you don't really need to know too much about this stuff unless you're using it directly. But feel free to jump in there and read that code. I'm not going to go through it, although some of you guys have asked questions about how do I make things happen with the mouse and move around and so on. And well, that needs to be done here in the app class controls. Like for example, if I process the mouse released, and I can use the arc ball and so on and so forth. Cool. I'm not going to go too much into that. If you have questions about it, please ask in the Discord or in office hours. All right, let's jump into the app class. So like the main, as we can see, our main class will go, it will create a new application and initialize it and then run. Let's go to the run function so we can see what happens. First, we're initializing it though, so let's go there. So when we initialize our function, our application, we set our initialization to, it should be false. We get our system singleton, we set the resolution, we set the name, and now we are initialized. Great. And below is just kind of a slightly better way to do it with the, if you're providing a specific height and size, which we're not doing. We're just providing this this size thing, this resolution thing, which will do it automatically for us. Great. So let's take a look at run. And run is effectively going to initialize our code. That's up here, which we've already done, I think, at this point, but whatever. And then we're going to go and run through the process. We're going to process the mouse movement. We can change the mouse, the position of the screen, all this great stuff. You'll notice too here we have display. If we go to display, that's going to actually go to our app class, and that's where we kind of hook into things. Great. And also init variables. When do we get our init variables called? Oh, that's going to be here in init. So see, this function will call our init variables as well. this is like a thing I like to do every time I go into a project that's not mine, that I didn't write the code. I kind of want to see how the flow works, how do I get to the different components, and if I don't really understand it from the code, I'll go and I'll debug it at that level. And so what we know now is that all the code that we really care about is in appclass.cpp. So init variables will set up everything that we want, like our camera, it'll create a new mesh, which will create this cone. When we update, we're going to call this function arcball, which will allow us to effectively move the camera around. So some people have asked this on the Discord before. Like, for example, if I get rid of arcball, I believe now if I try to rotate, oh no, it still will work. If I get rid of camera rotation, then I won't be able to rotate like I did before. And then the arc ball, I believe, is if I have an arc ball active on a particular object. So I can rotate that object, which I'm not going to go into, and that's beyond the scope of this particular thing. So great. So now we know this is where we're creating that cone. And so now it's clear that all of the magic is happening down here in our display. So let's go through this line by line, and we'll talk about what's going on. So first thing, we clear the screen. Clear the screen, as you know, just sets a color and clears it. We've done this in the past. Then our view matrix, this is going to go to our fragment and pixel shaders. We went through this in the last few lectures. This matrix is going to go into those shaders. We're not going to talk about the shaders anymore for a little bit. And so here we're setting the view matrix. We're getting that view matrix from the camera manager. And then we're also getting the projection matrix, which we're going to be talking about very soon, from the camera manager. So assume that all works. Great. Now we have to create a timer. So we're going to create a static float timer, and that's going to create a variable that's sitting there. Static means that every time we call this function, it's not going to reinitialize, it's just going to use the existing value that was there before. So this is how we can create accumulators. We've used this trick in the past. Then we're going to create a clock from the system. This is again, from the framework that Alberto has built. He's created a clock, and that way we can get this delta clock every time we call it. And so now we can add to the timer the change in time since the last time we called the clock function. So every time this function hits, we're going to increment our timer based on this value. So kind of like to show you guys a little bit of what's happening here, I'm going to go back into my code and hit a breakpoint. Now you can see that the F timer is 1.9, and when I increment 1, it's 1.906, and the next time is going to be much more because it's added that value to it, 5.9 and so on. So each time it's going to add the amount of time that has elapsed between. It's a bit hard to show this in debugger because when you hit the debugger, the clock doesn't stop going because it's using the system clock. Now we're going to create a list of stops, and these stops, you can kind of see them in the application. There are these little dots, the little spheres that are being created, which we'll see how that's done in a second. And so we're going to create one at -3, at +3, x, so those are these two, and then +2.5 and -2.5y. And you'll notice if I change this -3 to 6 or something, in theory this should all still work, but the value will be way over there. And you'll notice that when it's linear and interpolating a longer distance, it has to go faster, and we'll explain why that's happening in a second. Okay, we'll switch this back to 3. Now we're going to start at a start point and an end point, and we have this current route, and the route is going to represent the current value, the current route that we're going from, right? Which from which point we're going to which point we're now in. So you'll notice that the route is a static integer. And then to figure out the current route that we're on, the start point, it's just the v3 stop, this vector v3 stops, and the current index of the route. And then to figure out what our endpoint is, we're just looking at the next point in the route. However, because this is a vector, if we add one, we might be at the end of the vector, at the end of the array. If we're beyond the size of the array, we want to start back from 0. So this function, this line of code here, is a pretty eloquent way to effectively the modulo operator. Like it's kind of like the remainder. It's like if you divide 5 by 4 and you're going to be left with 1, so 1 becomes our remaining value. So this is really nice because the route can increment forever, and we can always get to where we want to go. So yeah, that kind of tells us, okay, our start value is here and our end value is there. Now this value gives us the amount of time we want between stops. So we want the cone to move between each stop. It takes 2 seconds. So assume if I wrote 10 here, for example, you'll notice this will go significantly slower, significantly slower. If I make this 0.1, now it will be so fast it'll probably be impossible to see. So let's go back to 2. And the way we find the percentage, right? So we have our timer, and then we have this function that I'll go into in a second, and then we pass the time between stops, and we want a value between 0 and 1. And this function, map value, is from the system definitions. This is, again, a framework function. And what it's doing is it's taking that value and mapping it to a scale and trying to figure out between 0 and 1 at what point we are in. And so what it's doing is it's taking the timer, right? This timer is just this number, and it's applying the values, trying to figure out the percentage of time between the previous stops. And the reason this works, yeah, that's kind of it. And so you can see, for example, when I go here, if I'm going to run this, let's see here, I'm going to jump into the code, and you'll notice that when I hit this float percentage, my time between stops is 2, and my timer is equal to 0.6099, and the time between stops is 2, and so I'm going to get a percentage of, for whatever reason, I'm in release mode, so it's getting rid of my values. Let me change to debug so I can actually see the values. You'll notice sometimes it's in release, you won't be able to get those values out of your program. Great, so now if I hit a point here, you can see timer is 0.46, time between stops is 2, and the percentage will be 0.23, because this 0.46 is 23% of 2. Now notice that this F timer is never going to be more than 2. And the reason for that is because down here somewhere, we're going to restart this clock. And it's going to hit to 0. And that way we can see, okay, every time we hit a stop, we're going to reset it. And so here's where we actually get the LERP function. Now we want to just calculate the current position between those 2 stops. So we have the start point and the end point, and we have the percentage along that we have, and then you just call this function LERP from GLM, and it will give you back a vector3, a GLM vector that is in a linear translation to that interpolated point. And then all we have to do, because we're not rotating the model or anything like that, we're just setting the model translation to that. And see here, if the percentage is greater than or equal to 1 or 100%, we now change the route, right? We increment the route and we make sure that the route is within the size. So if it's more than, the number of routes, then it goes back to 0 and we restart the clock. And that's it. That's all this code is. Actually, the LERP, now you can imagine putting as many stops as you want and you're going to get a thing that kind of follows a path as you'd like it to follow. And if you wanted to add, for example, a rotation, right, we can rotate the model even. We add GLM, rotate. We're going to do identity. We're going to rotate it some theta, vector, GLM vector 3. Let's rotate it about z. Right, and we're going to do static float theta. We've done this a million times. And now, in theory, our triangle. So you'll notice something interesting. Notice how our cone is not really rotating about the points that we defined. And this has to do with the fact, let's do it faster so that we can actually see this happening. Because I made a noob mistake. You'll notice that it's interpolating, it's almost like it's curving our translation. And why is that? Well, you probably guessed it by now, I'm rotating the translation. So the order in which you do these model transformations really matters. Because I want to think about the vertex is on the other side of this. It's like the model matrix times this. So if you can kind of imagine, first we apply the rotation, rotate, and then we translate. If you apply the translation first, and then you're rotating it potentially around not 0. So now hopefully our cone will rotate while translating. There you go. Pretty cool. That just about covers the LERP example. There's not too much else going on in here. The only other bit is we render the object. We also add the skybox to the render list as well as the sphere. So if you in theory, some of you guys have asked this question on the Discord. If you remove this code here, all you're doing is you're not going to render the skybox and you're not going to render those spheres. Cool. Great. Yeah, so that's about it for LERP. Now, let's move on to the next one, which is the rotations project. And this one should be pretty straightforward and pretty quick because for the most part, we've done a lot of this already. In fact, we did a little bit of it here. So similarly to before, we have the mymesh and the main files in here. I'm not going to go too much into how this project gets set up. We're just going to look at the app class because that's where everything is happening. So first, let's build it. No, let's not build all of it. Let's run it and build the project and see what happens. So now we've got a cone. It's being rotated about a point. Okay, so let's go through this again really quickly. We're taking the camera manager, we're setting up the camera, and then we're creating a cone. That's about it. In the update, all we're doing is we're updating the system, using the arc ball, which we're not using in this particular example, and we're updating the camera rotation as necessary. All the magic, again, happens in the display function of the program. So we start off, we clear the screen, we get the view matrix, we get the projection matrix, again, both from the camera. we set up a timer, and you'll notice that we do a lot of stuff with timers because timers give us an ability to move things around. If you don't, you can always do it frame by frame. However, if you do it frame by frame and you have an arbitrary frame rate, a linear motion is not going to be so linear. It's going to be based on the time steps between each one of the frames. So one frame takes, whatever, 10 milliseconds, the next frame takes 20 milliseconds, and the distance is the same, you're not going to get the same kind of uniform motion. So doing it with a timer is the right way to get what's called time-based motion versus frame-based motion. Depending on what you're doing, you may want to use one or the other, but most often you want to use time-based motion. And so, great. Now, what we're going to do is, so you've seen me use this a lot, this idea, static float theta equals 0, 0, 0f, and then theta plus equals to 0, right? So this is kind of the example I was saying. If I wanted to do a time-based move, a frame-based movement, I would do it this way because I'm adding to theta every single frame. It's very slow. And you'll notice maybe if I do it a little bit faster. It'll still look pretty okay, but it's not going to be time-based. So if I do something like this, you'll see it stop moving and start over again. Whereas if I go with the time-based approach, what you'll notice is even if I stop it, it'll show up where it should be. So okay, I stopped it for like a few seconds here. It'll show up on the other side. That's because it's time-based. It's calculating where it should be based on how time has elapsed. So what we're doing is we're creating a rotation matrix about the z vector, the z-axis, meaning we're rotating it about the z. And so we've seen this before. And the rotation matrix, keep in mind, we've had this talk about this a few times. The way you multiply these values really makes a difference. And then we have this matrix model, and because we're doing it outside of the for loop so that we have it outside, and the model matrix is going to be equal to the rotation matrix times the translation times the transpose of the rotation. And I guess what this is doing, so let's play with this to kind of understand it a little bit better. So say we only used the transpose. Oops. What would happen? We're now just using the transpose of the rotation. So this is kind of cool. So it's rotating, but in a way that actually is backwards. It should be rotating this way. And this is kind of going back to what we were talking about in lectures. The inverse transformation is the transpose for a rotation matrix, which is kind of fun. Now, say we did that, and then we translated. And so now, you'll notice that it's rotating over there. And that's because we're rotating the object, and then we're transposing it over there. You'll notice that a translate, and we're not transposing it, sorry, we're rotating it, then we're translating it over there. And if you wanted to do you wanted to inverse that, not translate, transpose. Now if we transpose it, instead of rotating this way, it'll rotate the other way. And now if we rotate that whole thing, so now we put it over here, and now we're going to rotate it around. And you'll notice that it rotates about that center point. Now you'll notice that that rotation about itself went away when we did that. So why is that? Say we remove this. What's going to happen? You'll notice that it rotates about itself in a way that maybe we don't want. We want it to stay still. So what you're noticing is when we rotate it that way, it also exhibits its own local rotation as well. If we want to eliminate that, if we want it to rotate but maintain its position, maintain its original orientation, we have to multiply it by that transpose. What you're doing is you're undoing the rotation locally. It's almost like you're compensating. It's almost like you're saying, okay, it's going to rotate this much because of that rotation. Let's undo that and then move it and then apply that rotation. So for example, if you wanted this to rotate kind of independently, you can then apply this here. And what you'll notice is that it will rotate about itself in this way, like before. But if you do it again, say if you do another one, it'll rotate twice. It'll almost seem like it's rotating about itself. So you can see how you can sort of composite these transformations as much as you want. And then the rest of this function is not really doing much. It's rendering the skybox, it's rendering the object, and it's rendering that sphere in the middle. And it's doing a little bit of debug output as well. So that's about it. Pretty straightforward. A lot of these functions you can see once we have the boilerplate stuff, once we have these basics built out, most of it's just kind of playing around, trying this, trying that. And it's pretty straightforward to kind of get to the next stage and adding more capability. Okay, so that's mostly it for the rotations project. Now let's move on to the scary one, Quaternions. So let's quickly just see what happens when we run the Quaternion example. I see. Okay, so what's happening here, I'll increase the size of the screen. You can see in the top left corner there's a little explanation. If you hit X, it'll reorient the model in X. If you hit Z, it's going to reorient us in Z. And then Y is going to reorient us in Y. Yeah, it's pretty cool. Sorry, I'm not able to use my keyboard apparently, so let me do this again. So this is Z, this is X, and this is Y. So you can see how all of these three are independent motions, and I can also move it with the keyboard a little bit, which is kind of a fun thing to do. You can see how the positioning and the orientation of it is independent. So to kind of let's look at the code. Again, we've got the same code structure, my mesh, and all that stuff. You'll notice that there's this new object that was loaded from file that is in here somewhere. So let's see how that was done. Perhaps and there was also textures and things like that. So this is kind of getting a little bit more advanced. You can see how the framework, Alberto's framework, handles this. You can actually create what's called a model. And this is coming from the Simplex framework that he's developed. And it's just downloading, it's loading it off of disk. And this is again something that's going to be in your in your repository. So if you go and you open up the repository, what you'll notice is there's going to be an include or data, objects, Minecraft. Here's our Steve guy. Great. And the textures are here. Anyways, it's getting a little bit ahead of ourselves. We don't need to really know too much about this at the moment. Just understand that that's how you load an OBJ, and that OBJs are a file format. We really haven't talked about meshes in terms of like file meshes and things like that. But just know this is how the framework allows you to load these off of disk in a way that is quite convenient. And in this sense, this object is no different than the cube or the sphere or any other kind of primitive that we've been using up until now. And if you want to add new ones, you just have to make sure that the files are where they're supposed to be. And I will say one last thing about OBJs is that, let's see, where is data? This is coming from, this is going to be coming from somewhere. Anyways, the data, the OBJ is really, if you open it up, let's open up Steve, it's just going to be a text file. So that's one of the reasons that OBJs are really popular, is all the data is right here. And the material, which is going to be in the same folder, is also just a text file. And so if you have any questions about what these things are doing, right, you can now see, okay, def Steve, here's our texture for Steve that's being used. Great. So we'll probably talk more about models in the future, but just so you know, this is sufficient for now. Now, also, we've moved a little bit of code into the update function, which is actually a lot more common. You don't usually put a lot of the orientation and that kind of functionality in your display or in your rendering. You kind of want to do it in update. That's because an update is a function that usually you're updating your engine separate than rendering. Rendering may take a fair bit of time, and objects may be rendered at different times in that pipeline. So you have like a really complex scene and game, and you have thousands of objects. So the first object may be rendered at one time, and the last object may be rendered 5 milliseconds later, which is okay because you know what the maximum time per thing. But 5 milliseconds may mean a lot for updating physics, updating the math, and updating other things that you want to keep track of. And so let's go through the update function, which has changed significantly now. First thing is we're creating this clock. So this looks familiar. We're creating a timer. And we're looking at the delta time. So this is how much time has elapsed between the previous frame. Now, we'll turn this on in a minute because we're not doing this yet. And right now, what we're doing is the matrix of Steve is going to equal to the 2 matrix of MQ orientation. What is MQ orientation? So now notice in our application class, we've added a member variable. So application class is up here in the header files. We've added a few things. We have the orientation quaternion. We have our mSteve. This is our model matrix for our Steve. And we have this model that we're saving everything to. And then we also have an orientation for the model in vectors, which we're using sometimes. And so here's the question, right? Is mSteve is being set? We're now using quaternions. And so the question is, like, how is this changing, right? Because all our display is doing is rendering our mesh manager, and that's it. our mesh is being added up here, so we don't have to worry about it. Right? Oh, actually, we're adding the model to the render list in update, so that's why it's catching it in the display. But for the most part, we're not seeing anything changing with like the Quaternion. But you notice that there are key combinations that I used to actually manipulate this Quaternion. So let's see where those are. They're not in here, but there's a file called app class controls. And here you can see that we do all this stuff, right? For example, when we push up the scroll, we move forward. When we push a particular key, we do these things. So the question is now, how are we handling the X, Y, and Z key downs? Well, it doesn't look like it's being done in here. Oh no, it is. Sorry. So down here in this file, there's a function called process keyboard. And first we have the process keyboard part that is changing our camera position. So here's the WSAD, that's moving our camera around. Q and E, that goes up and down. You can see it's just moving the camera vertically. And now we have this section here. And we have this MV orientation, X++. We're not using that yet. We'll use it in a minute. But here's the Quaternion code that when we hit X, what we're doing is we're creating a Quaternion about the X-axis with 1 radian. 1 degree, sorry. This is taking a degree and turning it into a radian. And so this represents a Quaternion rotation about the X-axis. And then we're multiplying our member Quaternion. Remember our app class here, it has this, and this function is in our application. So our app class is our class application. And we're applying that Q1 to it. So for example, let me do Z. So here, Z, if we hit the key Z, we're going to rotate about Z. So imagine if I was rotating 10 degrees, this would happen significantly faster. We can even do something a little fancy, right? And we can say, do float degree is equal to 1.0. And then we can say if SF keyboard is key pressed, SF keyboard shift, or left shift, then we can say degree times equal -1. Why? Expected a thing, great. Right? And then we put degree in here. And so now if I hit Z, it'll go this way. If I hit Shift Z, it'll go the other way. Cool. All right, that's a fun little hack. So now we know how this Quaternion, and also how the orientation is being set. It's being set in this class controls file. Great. So let's turn this off. So now we know how the Quaternion applications work. And you can see it's really simple. We take a Quaternion, we create it about an axis, and then we apply it to another Quaternion. And then when we want to take that Quaternion and turn it, that orientation, and turn it into a rotation matrix to be passed to our shader, we just call this function toMatrix of a Quaternion. And this is kind of how you can see this Quaternion becomes the orientation that it's very easy to manipulate. True. Or let's turn this to false. Now, let's try and do a translate vector orientation into a matrix. So now instead, we're going to use our orientation matrix. So this orientation matrix, what it's doing is it's treating X, Y, and Z as if they are Euler angles. And you can see what we do here. We create a matrix, a rotation matrix about X, a rotation matrix about Y, and a rotation matrix about z. And we just multiply them by each other. And if we do it this way, you'll see a very similar behavior. Basically the same. You'll notice also my shift still works in the same way. If I hit X, and if I hit Y, it all operates the same. But you'll notice something, right? Think about how much math is going on here. And you still need to do this. This isn't even using it. No. We don't want this. Well, of course it's the same. It wasn't even working. Let's do it. Let's actually do it this time. So again, it should be the same for the most part. Cool. Right? Pretty cool. Fun. You'll notice these strange behaviors though, and this is something that's kind of important with the different orientation and the different rotation matrices and the other guys. But for the most part, it should work relatively the same. Great. So yeah, that's actually now using this, and you can see the way we're doing this orientation matrix. It's effectively an Euler, it's a set of Euler rotations. And each one of these is a rotation about the x vector, the y vector, y unit vector, and the z unit vector. Great. Now let's do slurp. And what this is going to do is it's going to rotate from one quaternion to another quaternion using the slurp function, or specifically the mix function. And the way we're doing it is we're going to map the timer from 0 to between 5 to a 0 to 1, and then that's going to determine our percentage of mixing from Q1 to Q2. And Q1 in this case is not being set to anything, so that's your identity quaternion, or the original orientation of the quaternion. And then we're going to rotate it about Z up until 359.9 degrees, so effectively 360 degrees. So let's see what happens here. And you can see now it's going to rotate about itself. Now there isn't a visible jump between 359.9 degrees and 360. However, there is a jump, and we can see that jump if we were to, say, end it at this point, and it'll kind of click in. This is a really important thing about quaternions, and you'll see it kind of hop. Maybe it's still not distinct enough. Let's do 300 degrees. It should be around here, I think. No? Okay. I'm really trying to show this jump. Okay. Clearly I don't know what I'm talking about. There should be a jump, but there isn't. Let's see, 90 degrees. Should it even work at all? Right. Okay. So this sort of refers to the nature of quaternions. What's happening here is you're starting off with the original orientation of the object, and so there is no value to Q1. It's like the identity. So you're starting off with wherever it is right now, and then you're going off and applying a 90-degree rotation to it with a particular intensity, because that's the amount of time it should take. So there is not going to be a jump, because when it gets to 90 degrees, the next time it's going to rotate in that direction anyways. And so there's never actually going to be a hop. And this is sort of what I was saying in the lecture. If you're doing an accumulation, this is what's going to happen. You're going to have error. And I'm kind of showing where the error is here by way of the fact that there is no actual interpolation. It's just going in a particular direction. You don't have a start quaternion and an end quaternion. We might be able to do this. Let's try this out. Let's see if this produces what we're after. Nope. Anyways, the point is that a quaternion is a relative. You're starting from a point, you're going to a different point. So it's not actually possible to make them absolute. You are, in a way, a quaternion is kind of like a vector for a orientation. So in a way, if I do this, right, where I go static start quaternion, this may give us the jump that we're after. Nope. Not really what I meant to do. We don't add them. All right. Give up. It just goes to show. I don't know what I'm talking about with slurp. I hardly ever use slurp personally. They're a little bit hard to use in this sense. But you can kind of see how you can go from one rotation to the next, and with a very nice sort of interpolation of those things. Yeah. I guess one thing I would do actually is you could do it that way maybe. Okay. Clearly not. Clearly I don't know what I'm talking about. Anyways, you can kind of see how these are useful. That's about it. Like, this is sort of it. Kind of explains how you would use this stuff in practice with a variety of different ways. You can either use a quaternion to rotate, to set your orientation, and to kind of have an absolute sense of orientation. Or you can use a vector representing the X, Y, and Z rotations that are like the Euler angle rotations. then I'm creating a matrix of each one. You can also use the Rodriguez formula to do it all in one. You don't have to do it like x times y times z as we were talking about in lectures. You can also use SLERP to interpolate between variety of different quaternions. Actually, yeah, and that's sort of a good overview. One thing maybe we can show is the nonlinearity of doing this mix with a rotation matrix. So let's go ahead and try that out. Let's create a new section here. Call it LERP true. And let's just do a rotation about z, where we have a rotation of rotation 1 and rotation 2, and this is going to be just 0, although technically this could be just the identity, and 2, which is going to be really we're going to do what we're doing up here, which is 359.9f. Great. Then we're going to recreate here the percentage. So we're going to rotate every 5 seconds. And then we're going to now create a auto M4 rotation is equal to GLM LERP of M4 orient Z1 to M4 orient Z2 with the percentage number. And then we're going to set msteve to be the M rotation. And so this is going to linearly interpolate those two matrices. Apparently I can't LERP it, a matrix, because it knows better than me, so I'll use mix, which is very similar. All right, so now what we want to see is it not working as usual. Let's see here. Let's see if this. Right. So the reason that it wasn't working before is you can kind of imagine the rotation of 359 to 0. It's trying to go just to that next point in a way that Quaternions is actually applying a delta in a direction. But so doing a 90-degree will show you the problems with that, how a LERP doesn't work for rotation. You can see this nonlinearity being introduced to the point where we are going to get to that rotation, but it's gonna cost us. It's gonna look weird, and it's gonna do some strange things. So yeah, kind of demonstrates how this does not work. Cool. All right. Hopefully this kind of gave you an overview of these different projects, and will put you in a good position for this week. All right. Thanks for watching.